Hello everyone, my name is Ajit Agrawal. We are going to study semiconductors. In semiconductors, first of all, we are going to study electrical properties of solids, then intrinsic semiconductor, then doped semiconductor, diode, and transistor. So first of all, we shall start with electrical properties of solids. Macroscopically studying how will a solid behave will depend upon its resistance. Now it is very obvious, if a body has zero resistance, then infinite current can pass through it. Therefore, we call that as superconductor. But if the resistance is finite, then finite current will pass through it, and such a solid is called conductor or a semiconductor. But if resistance is infinite, then practically no current can pass through it, and such a solid is called insulator. Microscopically studying, we have three factors that determines whether a solid is superconductor, conductor or semiconductor. The first one is their resistivity. The second one is temperature coefficient of resistivity. And the third one is the number of charge carriers per unit volume, small n. We shall remember this one, small n. So, I am taking two materials, one is copper and other is silicon. The resistivity of copper is 2 into 10 power minus 8, while that of silicon is 3 into 10 power 3. So we can see that silicon has very high resistivity, therefore it will have very high resistance. So it is a bad conductor. Temperature coefficient of resistivity for copper is 4 into 10 power minus 3. So if I increase the temperature of copper, then its resistance will increase, thereby decreasing the conductivity of copper. But that of silicon, it is high and negative. That means for silicon, if I increase the temperature, then its resistivity will decrease. Number of charge carriers per unit volume. Now for copper, that is 10 power 28, and this is very high value, and that makes copper very good conductor. But that for silicon is 10 power 16, very less. That's why silicon is a bad conductor. When I say it is a bad conductor, I do not mean that it does not conduct. It does conduct, but the conductivity is not very high. Now I shall attempt to explain the difference in electrical properties of copper and silicon by Bloch's theory. First of all, copper. We can see copper has 29 electrons and it is arranged in its orbital as shown. We can see 4s has only one electron, and this 4s could have occupied 2 electrons. So this one electron can go to another location in 4s itself by changing its spin, and the energy required to do so is only 0.05 electron volt. And we know that this energy is easily available at room temperature. I shall explain you how. The energy of an electron at room temperature is 3 by 2 kT, which is 0.04 electron volt. But we need 0.05 electron volt. But we also understand that this 3 by 2 kT is only an average value. That means most of the electrons will have energy more than 0.04 electron volt. So they will easily change its spin and go to another location in 4s itself, while still remaining in 4s orbital. So that makes a copper atom very good conductor. Now let's see how copper atom is arranged in a lattice. In a solid copper, the distance between adjacent copper atom is 260 picometer. When two copper atoms are very far apart, we can see this distance r is very large as compared to 260 picometer. We want to understand what will happen when these two copper atoms come close to each other. If we bring two copper atoms close together, then 1s of one copper atom will come very close to 1s of another copper atom. But these two 1s level will not overlap with each other. If they do so, it will violate Pauli's exclusion principle. I hope you remember what is Pauli's exclusion principle. Pauli's exclusion principle states that no two electron can occupy the same values of all the 4 quantum numbers. Therefore, 1s of one copper atom cannot have the same values of all the 4 quantum numbers as 1s of another copper atom. And same thing will happen with 2s, 2p, 3s, 3p, 3d and 4s. They will all split to two levels. Or I can say it is like 1s and 1s dash, 2s and 2s dash, 2p and 2p dash. And this process is called splitting. So instead of having 29 electrons, we are having 58 electrons. So we will have 58 quantum states available right now. Now in solid copper, there are many copper atoms. Let's say n. We want to understand what will happen if these n atoms come close to each other. Then instead of having one 3s level, we will have n 3s level, n 3p level and n 4s level. And such a level is called energy band. So instead of calling n energy levels, we call it as n energy bands. Or we can think that 3s energy level split itself into n levels. When this will happen, we can imagine that there will be a region of space where you can find electrons. And the separation between two consecutive energy bands is called band gap. I shall show you the same in the energy diagram. In this diagram, I haven't shown all. I have shown from 3p and 3d, 4s and 4p. As you can see, in 4p, I have shown very clearly that this 4p has split into n energy levels. And they are very, very close to each other. And this process is called splitting. And as we have in 4p, we shall also have in 4s, 3d and 3p and all the energy levels below this. We can understand that in 4s, we had one electron. So when we have n copper atoms, we have n electrons here and n empty spaces. Because we have n electrons here, it is wise to call it a valence band. But because we have empty spaces, we also call it as a conduction band. 4p has no electron, so we safely call it as a conduction band. While 3d, the entire level is filled with electrons, therefore we call it as a valence band. And this entire thing is the region of space where we can find electrons. The separation between these two is called band gap. Now suppose I draw these three, that is 4p, 4s and 3d in a single diagram. How will it look like? So this is how it looks like. 4s is the valence band and the conduction band. And above this we have the conduction band, which was 4p, and below this we had the valence band 3d. Now since in metal the valence band and conduction band overlap, therefore electrons have a lot of space to move and hence they are good conductors. Now we shall see insulator. As you can see in insulator, the band gap between the valence band and conduction band is very large, which is of the order of 6 electron volts. Therefore the electron from the valence band of an insulator has to jump to the conduction band, which requires 6 electron volt, and such an energy is not available at room temperature. Therefore it will be hard for electrons to jump and conduct, and that's why we call such a solid as an insulator. Semiconductors. In semiconductors, this band gap is not very large. For silicon, it is of the order of 1.1 electron volt, and for germanium, it is 0.7 electron volt. Now, to jump from valence band to conduction band, energy required is 1.1 electron volt for silicon. And at room temperature, we have only 0.04 electron volt. But we remember, this is just an average value. Thus, there will be some electrons which will have energy more than 1.1 electron volt, and such an electron can easily climb up from the valence band of silicon to conduction band of silicon. But at the same time, we should understand that at 0 Kelvin, the electrons will have no energy, so the same semiconductor will behave as an insulator. Now we shall first define intrinsic semiconductor. Semiconductor without any impurity is called intrinsic semiconductor. Now we shall stick to silicon in all our upcoming slides. We know that in a silicon lattice there are 10 power 28 atoms per meter cube arranged in a tetrahedral structure. You can see this. This is a tetrahedral structure. So they are arranged like this, and to understand this it becomes very tough. So what I have done, I have drawn this diagram to understand the behavior of silicon. The electron in an isolated silicon atom, whose atomic number is 14, is arranged in a subshell with a scheme 1s2, 2s2, 2p6, 3s2, 3p2. Now we can see that there are 4 valence electrons in silicon, and we can see in this structure that there are 4 electrons which are bonded to another silicon to form an octet. I have shown here an intrinsic semiconductor of silicon at 0 Kelvin. But what will happen if I raise the temperature to 300 Kelvin? I have shown this in the diagram. This electron, which was in the valence band of silicon, has gained energy and it has climbed up to the conduction band of silicon. But when that happens, it leaves behind a hole. And this electron is right now in the conduction band of silicon. Because I did not have any place to show, I have shown here. At 0 Kelvin, the electrons are immobile, but when we raise the temperature, the very same electron gains thermal energy, causing the electrons to jump to conduction band and simultaneously leave behind holes in the valence band. Now this is a key statement in this chapter. Electrons jumps to the conduction band. With this statement, what I mean is in conduction band, we'll talk about only electrons. I can show you in this diagram. You can see these red ones are electrons in the valence band of silicon. Now they can easily climb up to the conduction band at room temperature, at least some of them. So when it happens, it leaves vacant space, which we are calling as holes. So in effect, what I am saying is in conduction band, we shall talk only of electrons, and in valence band, the vacant space we are calling as holes. Now reason for conductivity of semiconductor is because of the electrons in conduction band and the holes in the valence band. This process is called thermal generation of mobile carriers. According to Boltzmann's statistics, this thermal generation is proportional to e to the power minus Eg by kT. This Eg is the same band gap, 1.1 electron volt for silicon. And as we raise the temperature, the thermal generation will increase according to Boltzmann's statistics. Now in an intrinsic semiconductor, the number of free electrons in conduction band should be equal to number of holes in the valence band, because the electrons which climb to conduction band has left behind holes in the valence band. Therefore Ne will be equals to Nh, which I am calling as Ni. Ni is number of charge carriers per unit volume. If you remember the previous slide, it was 1.5 into 10 power 16 for silicon. After the electron goes to the conduction band, they do not stay there forever. They come back to the valence band to recombine with the hole. And when this happens, if you remember Bohr's theory, if an electron from higher energy level comes back to lower energy level, a photon will be emitted. But at this point of time, we are not interested in those photons. We just want to understand how these electrons will behave. We'll come to photons in later sections. So these electrons do not stay there forever, and they come back. And simultaneously, newer electron goes to the conduction band. The process of coming back is called recombination. Now this recombination requires that one electron combines with one hole. So therefore recombination rate must be proportional to Ne into Nh. But we know that Ne is equals to Nh is equals to Ni. Therefore recombination rate is proportional to Ni square. At equilibrium, the generation rate is equals to the recombination rate. If generation rate is greater than recombination rate, then number of electrons in conduction band will keep on increasing, making it a good conductor, which is not the fact. And if recombination rate is more than generation rate, then number of electrons in valence band will keep on increasing, making it an insulator, and this also doesn't happen. So at equilibrium, the generation rate must be equal to the recombination rate. Now, since generation rate is equals to recombination rate, so I can say that generation rate is actually proportional to Ni square. and for silicon, Ni is 1.5 into 10 power 16 per meter cube. Now we want to understand how we can increase semiconductors' conductivity. By increasing the temperature, I can reduce the resistivity of semiconductor. And I hope it is very clear, because when I increase the temperature, 3 by 2 kT, which was 0.04 electron volt at 300 Kelvin, now it will be more than 0.04 electron volt. So the same semiconductor behaves as a good conductor. Another way is by applying an external electric field. An external electric field applies force on the electrons in the valence band of silicon, and they can climb up to the conduction band of silicon provided the electric field is good enough. By shining the light of proper frequency, we know that if a photon strikes an electron, the electron gains the energy, and if the energy is sufficient, it can climb up to the conduction band. But at the same time, we should not expect at 0 Kelvin for the electrons to have any energy. Thus, they cannot climb to conduction band. Therefore, a semiconductor is an insulator at 0 Kelvin. Now we shall try to understand how to increase the semiconductor's conductivity in external electric field. To apply the field, I have chosen the battery, and the battery will apply the electric field to the right. Now we remember, at room temperature, the electrons were at conduction band and the holes were at valence band. The force on the electrons will be to the left, while the force on the holes will be to the right. In both the cases, the current will move to the right, so the net current will be equals to IE plus IH. The current density was NEV, so the net current density is going to be NEE VDE plus NHE VDH. A side point, the drift speed of electron is going to be more than the drift speed of holes. The reason being, in conduction band, there were no electrons present. So the electrons in conduction band have a lot of space to move, while the holes in valence band are restricted. Therefore, the drift speed of electron is more than drift speed of holes. At the location of holes, actually they are nothing. We still assign some mass there, and we say because the speed is less for holes, the mass is more. We will have conductivity as NE mu E plus NHE mu H. We can remember this one. Now we want to understand extrinsic semiconductor. It is very obvious that if we add some impurity, then it is an extrinsic semiconductor. The process of adding the impurity is called doping. For every 10 power 7 silicon atom, we have just one impurity. We remember that there were 10 power 28 silicon atoms per meter cube. That means there will be 10 power 21 impurity atoms per meter cube. Such a material are of two types, N-type and P-type, which we will see just now. N-type semiconductor. Suppose I add phosphorus as an impurity in silicon lattice. Phosphorus has atomic number 15, so we are left with 5 valence electrons. Then what I have shown is one of the phosphorus atom replacing the silicon atom in the lattice. Now since phosphorus has 5 valence electron, the 4 are bonded to the respective silicon atoms to form the octet, and the 5th electron is with phosphorus itself at 0 Kelvin. But what will happen if I increase the temperature? Energy required to make them free is 0.05 electron volt only, and this we know is automatically available at room temperature. And if this will happen, the donor side, that is phosphorus, will become positively charged because it has lost one electron, and the entire material will still remain neutral. Since the negative electrons donated by impurity enabled the material to conduct, therefore it is called N-type. N refers to negative electrons which were donated by phosphorus. Since at room temperature, the 5th electron from the valence band of phosphorus easily reached the conduction band of silicon. That means the valence band of phosphorus should be very near to the conduction band of silicon. Or to say the band gap between them should be of the order of 0.05 electron volt. And I've shown this in the diagram. Here you can see that this is the energy level of phosphorus. And this band gap is of the order of 0.05 electron volt. If you notice, I've shown this energy level by dotted line. I've done this because these phosphorus atoms are localized. They are not at every location in the silicon lattice. This phosphorus atom is called donor atom because it easily donates an electron to the conduction band of silicon. At the same time, the electrons from the valence band jumps to the conduction band of silicon. Therefore, the number of electrons in conduction band of silicon is very high. And that will also leave some holes in the valence band of silicon. Because the number of electrons in conduction band of silicon are very high, therefore electrons are called majority carriers. These holes are also conducting electricity, as discussed earlier, but since they are very few in numbers, they are called minority carriers. Now we shall see the entire thing once again. There were 10 power 28 silicon atoms per meter cube. That means there were 10 power 21 phosphorus atom per meter cube. And every phosphorus atom donated 1 electron. Therefore, there are 10 power 21 electrons per meter cube. Also, there were thermal electrons already present in the conduction band of silicon, which were 1.5 into 10 power 16. So the total number of electrons in the conduction band of silicon will be this. At the same time, we also remember that this generation rate was proportional to Ni square. So I am saying the new recombination rate should be Ne dash into Nh dash. Why I am writing dash? Because Ne dash, which is this, has changed. At equilibrium, the generation rate and the recombination rate must be equal once again for the same reasons which I have explained earlier. Therefore, Ni square should be equals to Ne dash into Nh dash. Now let us conclude this n-type semiconductor. We had 10 power 28 silicon atoms per meter cube, and there were 1.5 into 10 power 16 electrons per meter cube donated by silicon. But phosphorus were 1.5 into 10 power 1 atoms per meter cube, and every phosphorus donated 1 electron. Therefore, the total number of electrons in the conduction band of silicon is 1.5 into 10 power 21. And we have derived that number of holes in the valence band of silicon is Ni square by Ne dash, and if I put value of Ni and that of Ne dash, then we can get what is Nh dash, and we end with this value 10 power 11, which is a very small number. And that is why this is called n-type semiconductor, because the number of electrons are 10 power 21 and number of holes are 10 power 11. Because the number of electrons are 10 power 21, therefore it is called majority carriers, and because the number of holes are 10 power 11, it is called minority carriers. P-type semiconductor. Now in silicon lattice, if I add aluminium having the same ratio 1:10 power 7, the problem is aluminium has only 3 valence electrons, so it will leave one hole at this place. Now this hole can be filled by an electron from the adjacent silicon atoms. Thus these aluminum atoms are also called an acceptor atom. This makes aluminium negatively charged because initially it was neutral, but the entire material will still remain neutral. Now the electrons were coming from valence band of silicon, and it can easily jump to the valence band of aluminium, and the energy required to do so is only 0.05 electron volt. Therefore, the energy level of aluminium should be close to the valence band of silicon. As you can see here, this is the energy level of aluminium. Therefore, holes are created here. That makes the holes the majority carriers and the electrons the minority carriers. Because holes are the majority carriers, therefore it is called a p-type semiconductor. Diode. Diode is a device where p-type semiconductor and n-type semiconductor are joined together, as we can see here. And the symbol for this is this. The left one is the p side and the right one is the n side. We'll first examine the motion of majority carriers here. and then the minority carriers. Open circuited PN junction diode. By this, what I mean is that I have not connected any battery. Now, everyone knows what is diffusion. When there is a concentration gradient, then from high concentration to low concentration, the particles will flow. Now, in this semiconductor, on the P side, we have holes as the majority carrier, and on the N side, we have holes as the minority carrier. So, holes from P side will diffuse to the N side. And of course, if that will happen, the current will flow from P side to N side, to the right. And this current we call as diffusion current. At the same time, we understand that on the N side, electrons are the majority carriers, and on the P side, electrons are the minority carriers. So the electrons from the N side will diffuse to the P side. And if the electron is moving to the left, the current will move to the right. So in open circuited PN junction diode, holes are diffusing from P to N and electrons are diffusing from N to P. But for both of them, the current is to the right. That is I diffusion. And this will happen only at the junction because the concentration gradient is only at the junction. Now when the electrons move from N to P and the holes move from P to N. On the N side, the semiconductor has lost an electron, so this location should become positively charged. At the same time, this location has gained electrons, so this junction should become negatively charged. When this happens, the junction at P side also becomes devoid of any more charge carriers, since the octet at the junction is complete. You can see again, and on the N side we have positive charge and on the P side we have negative charge. So this will create an electric field to the left, and if the electric field is to the left, the potential will decrease in the left direction. Now this region is called depletion zone, whose width is of the order of 0.5 micrometer. Now we shall see the motion of minority carriers. We understand that there is an electric field that is created in the left direction. Now on the P side, electrons are the minority carriers, and on the N side, holes are the minority carriers. Now this electric field, it will apply force on the holes to the left, that will cause the current to the left. Now this very electric field will apply force on the electron to the right, and that will cause the current to the left. Now this will reduce the width of the depletion zone by some amount, because this electric field in turn is also causing diffusion current to reduce. The matter of fact is, both diffusion current and drift current takes place simultaneously. Initially, only diffusion current is there, but because of diffusion current, the electric field develops in the left direction, and that causes drift current to flow. Slowly what happens, the diffusion current reduces and drift current increases, and at one moment both of them are equal. Now obviously, because there is an electric field to the left, there is a potential difference delta V. For silicon, this potential difference is 0.7 volt, and for germanium it is 0.3 volt. Now we want to understand when the charge density on N side is twice that of the P side. Now if the charge density on N side is large, the electrons will be very close by, and because the charge density on the P side is less, the holes are far apart. Now what I understand is the electrons from N side will diffuse to the P side. When this is happening, because the number of electrons on N side is twice that of the number of holes on the P side, these electrons have to go twice as far on the P side. Because on the N side the concentration gradient was high, therefore the width of depletion zone on the N side was small. So we will remember this, we have to use this later in the chapter. Closed circuited PN junction diode. Now we want to understand what will happen when we connect a battery to the PN junction diode. As you can see, the positive terminal of the battery is connected to the P side and negative terminal of the battery is connected to N side. Such a kind of connection is called forward bias, I'm assuming that I have taken a silicon diode, and the potential difference here is more than 0.7 volt. Why I am saying that? Because if you remember, the potential difference across depletion zone was 0.7 volt. Unless you connect a battery of EMF more than 0.7 volt, no current will flow. Now, because the potential difference across the battery is more than 0.7 volt, the electric field that will be created by battery will be more than the electric field at the depletion zone. So the net electric field is going to be to the right. Because the net electric field is to the right, therefore the holes on the P side, which we are not able to diffuse to the N side, will easily diffuse to the N side. And the electrons which were on the N side will diffuse to the P side. Now, because the holes have gone to the right, the current will be to the right. And because the electrons are going to the left, the current is going to be to the right. So, this is going to increase the diffusion current. Since the number of minority carriers are very less, the drift current doesn't change by significant amount. The reason for I drift is not how fast the electron crosses the junction, but how often they do so. Because the number of minority carriers are very small, therefore they will not cross the junction very often. So the drift current does not change by significant amount. Therefore, the net current is going to be I diffusion minus I drift. I am going to present to you a second argument on the same case, which is very useful to understand further. On the P side, we have holes, and these holes will be repelled by the positive terminal of the battery. And on the N side, we have electron, which will be repelled by the negative terminal of the battery, and so the electrons will move to the left. And therefore, the net current is going to be to the right. Therefore, at equilibrium, the net current is going to be I diffusion minus I drift. Reverse bias. Now in this you can see the P type is connected to negative terminal of the battery and the N side is connected to the positive terminal of the battery. Now what will happen? Because of the battery, the electric field will be to the left and there was already an electric field due to the depletion zone. Because the net electric field is to the left, the diffusion current will reduce. And because the drift current does not change by significant amount, therefore, the net current is going to be I drift minus I diffusion in anticlockwise direction. And this net current is called leakage current. What will happen that the electrons on the N side will be attracted to the positive terminal of the battery and holes on the P side will be attracted to the negative terminal of the battery. This will increase the width of the depletion zone. Now I am concluding this. We have seen two kinds of closed-circuited PN junction diode. One is the forward bias and the other is the reverse bias. In forward bias, the current was I diffusion minus I drift. And in the reverse bias, the current was I drift minus I diffusion. The reverse current is very, very small, while the forward current keeps on increasing the potential difference across the battery. I have shown here V diode 0.7 volt. Only after we apply 0.7 volt, the current will start to flow. We can also see that this graph is not a straight line, therefore it does not obey Ohm's law. And now we shall study the application of diode. Half-wave rectifier. As you can see, we have applied an AC source here and there is a diode. When the current is clockwise, the diode allows the current and we can take the output here. And when the current is anti-clockwise, the diode does not allow the current, therefore the output will be 0. I am showing you the same in the graph. This is the input and this is the output. As you can see, when the current was anti-clockwise, the diode did not allow any current to flow. So this is AC while this is DC. Because it corrects only half cycle of AC, therefore it is called half-wave rectifier. Full-wave rectifier. As you can see here, once again this is AC this is a mutual inductance that I am trying to show here. It may be in same sense or it may be in opposite sense. Now because of the AC, in one cycle the current will flow in clockwise direction. It cannot flow through D2 because D2 will not allow current to flow, and we can take the output across the resistance R. In the second cycle, the current will go in anti-clockwise direction, and once again you can see the current through the resistor is to the left. So because the direction of current through the resistor is to the left in both the cycle, therefore it is fully rectified. And we can see here in this graph. This time period is T, so the half time period is going to be T by 2. And because the time period is T by 2, the frequency has to be 2f. There is another case of full wave rectifier. In the positive cycle, the current is going this way, and in negative cycle, the current will be going this way. In both the cycles, the current is going to the left, so we have a full wave rectifier. Filtering circuit. As you can see, this is a full wave rectifier through which the current will go in the left direction. Because the current is going in the left direction, this location is at high potential and this location is at low potential. Now we will take the output here. Let the output of full wave rectifier has time period of 0.01 second. But this rectification is oscillating, which cannot be used to run electrical devices. We need a steady output. For that we connect a high value capacitor C across RL. Let's say the time constant for this circuit is 0.05 second. In 0.01 second, we can always calculate that the charge retained by the capacitor is 99.33%. That means the potential difference across the capacitor is practically constant because the charge of the capacitor is practically constant. And hence the output will be as shown. Breakdown in diodes. In reverse bias, if we apply a voltage beyond a certain voltage, a breakdown occurs and the current suddenly increases to a very large value without changing the voltage by a large amount. The same thing happens in forward bias also, but I have not shown here in this diagram. And this breakdown has a lot of practical applications which we are going to study now. The voltage before the breakdown is called knee voltage or cut-in voltage. There are two kinds of breakdown, avalanche breakdown and Zener breakdown. Now I have shown here, in case of Zener breakdown, we use it as a Zener diode. In reverse bias, we use diode as a photodiode or a solar cell, and in forward bias, we use the diode as an LED. Avalanche breakdown. Avalanche breakdown occurs in a lightly doped PN junction. I hope you remember, if it is lightly doped, the depletion width will be large. Now electric field is given by minus del V by del X. So if the depletion width is large, the electric field is going to be small. So to create a larger electric field, we apply a larger potential difference EMF. And because of that, the electric field at the junction becomes very high and it causes the electrons to get ionized. And when this happens, it leaves a hole behind. But it just doesn't happen with one electron, it happens with many electrons and many holes. And this very same electric field will accelerate the electrons as well as holes. This may result in rapid increase in the reverse current. Therefore, such a breakdown is called avalanche breakdown. Breakdown does not mean that diode is damaged. The process of avalanche is not destructive. Zener breakdown. The Zener breakdown occurs in a heavily doped PN junction. Now if it is heavily doped, the depletion zone is going to be thin. It is so thin that the charged particles cannot accelerate enough to cause collision ionization. Now because it is thin, therefore dx is small, therefore electric field is going to be large. So lesser external electric field is required, which is usually around 6 volt but below it. Thus, because of high electric field, large number of electrons easily jump from the valence band to conduction band. So those many holes are also created in the valence band. And if the number of electrons and holes increases, it will easily conduct electricity. Zener diode. This is the symbol of Zener diode. The Zener diode, it not only allows current to flow in forward direction, but it also allows the current to flow in reverse direction. But what we do is operate the Zener diode in reverse bias. For Zener diode to function, the applied potential difference should be around 6 volt but below it. You can see the graph. This is the region where Zener diode functions, and you can see we don't have to change the voltage by a large amount, but still the current shoots to a very high value. We provide the input from a filtering circuit so that potential difference remains almost constant around 6 volts, and the current will go in this direction. But the potential difference across the diode is not going to change by a large amount, even if the current changes by a large amount. The output voltage that we take across the load resistance is going to be constant. That is why Zener diode is used as a voltage stabilizer. LED. We have seen brightly colored electronic numbers glowing in alarm clocks, invisible infrared beams that control elevator doors. In all these cases, the light is emitted from LED. Now, our point is, how can semiconductor generate light? And I hope you remember, in a semiconductor, when an electron from conduction band falls into a hole at valence band, a photon of energy Eg is released. Now, in intrinsic semiconductor, we had 10 power 16 electrons and 10 power 16 holes. So therefore, 10 power 16 electron hole pairs are not sufficient for the light to be intense enough to cause the numbers to glow. Suppose I take an N-type semiconductor. Here we have 10 power 21 electrons, but here we have only 10 power 11 holes. So, recombination will occur only for 10 power 11 holes, and the intensity becomes even lesser. So what we do is we take PN junction diode. Now in PN junction diode, what is the advantage? On P side, we have 10 power 21 holes, and on N side, we have 10 power 21 electrons. So when the holes transit to the N side, 10 power 21 recombinations takes place per meter cube, and that makes the light intense enough. The way we do is we attach a battery in forward bias. The holes on the P side will be repelled because of battery's positive terminal, and the electrons on the N side will be repelled by the negative terminal of the battery. So holes on electrons combine here, and therefore the light is emitted. And this is what is the symbol for an LED. This you can remember. For different voltages, we have different colors that is being emitted. Photodiode. Now, just as passing current through a diode produces light, similarly, passing light through a diode produces current. This is the basis for photodiode. Example, TV remote is LED, but circuit in TV is a photodiode. Because you pressed a button in TV remote, and it emits an infrared radiation which is accepted as a coded sequence of pulses by the TV itself. And that TV has a photodiode. And this photodiode deciphers the coded sequence, which can help in changing channel or adjusting the volume and other tasks. When a PN junction diode is illuminated with light, electron-hole pair are created, due to which additional current begins to flow. And this current is solely due to minority charge carriers. Why this happens is because we operate the photodiode in reverse bias. A photodiode is used in reverse bias since in reverse bias it is very easy to observe the change in current with the change in intensity of light. Therefore it is reverse bias and the current is flowing in reverse direction. The symbol for photodiode is this. Solar cell. Now this figure shows a PN junction diode connected across a load resistor R. Now throughout the diode we shine light. And when we do that, an electron-hole pair is generated. Because the electric field is in upward direction, causing the current to flow in upward direction. And this is what is the principle of solar cell. Because the current is flowing from N to P, therefore this is a reverse current. Now we shall try to understand this further. At equilibrium, I diffusion was equals to I drift. But after the light falls on the diode, drift current increases. I can say that entire graph moved down. And the net current is I drift minus I diffusion. So a better way to represent the same graph is this. Now we can take power output from the solar cell or through the bulb that I had connected. And the formula for power is I into V. I want to maximize the power. So what I do is choose a point here such that the current is maximum and the voltage is maximum. Because the current is maximum and voltage is maximum, the power output will be maximum. Before we move into transistor, first we will define the resistance in semiconductor devices. The current voltage relationship of a diode is not a straight line, thus it does not obey Ohm's law. Due to this non-linear nature of the curve, two types of resistances in PN junction diodes are defined. The first one is static resistance. Static resistance is defined when a semiconductor device is connected to a DC circuit. And another one is dynamic resistance. Dynamic resistance is defined when a semiconductor device is connected to an AC input. The resistance of a semiconductor device keeps on changing when an AC input is applied. Therefore, we define dynamic resistance. Let's see how to calculate static resistance. In this case, current is 2 milliampere, while the voltage is 0.6 volts. So resistance will be 0.6 volts by 2 milliampere, and that gives me 300 ohms. Now let's see how to calculate dynamic resistance. Suppose I want to find dynamic resistance at any instance. What I will do, I'll take the slope in IV graph, and that will give me the dynamic resistance R. The slope will be del V by del I, which is tan theta. And because it is IV graph, theta will be from vertical. So we can understand at different locations, the dynamic resistance is going to be different. Transistors. Now in this NPN transistor, we can see this left one is emitter, which is heavily doped. The middle one is base, whose thickness is of the order of 1 micrometer, and it is lightly doped. And this is collector, which is moderately doped. The symbolic representation of the same is over here. This transistor, it has 3 terminals. But to operate the transistor, we need 2 input and 2 output terminals. So what we do is we take one terminal common in input and output. Similarly, we have PNP transistor. It also has emitter, base, and collector. If you notice, the direction of current in NPN transistor and PNP transistor are different. In NPN, it is from base to emitter, while in PNP, it is from emitter to base. Common emitter NPN transistor. Now, we can analyze a connection for a while. You can see that this portion is emitter and it has one terminal over here. This portion is base, there is another terminal here, and this one is collector. So what I have done is I have taken emitter terminal common for the input and for the output side. There is a battery Vs and there is a high potential difference VCC which is connected over here. We shall now try to examine these currents IB, IC and IE. If you see carefully, this portion looks like a forward bias to me because the P side is connected to positive terminal of the battery and N side is connected to negative terminal of the battery. We will try to understand how the current flows in this. The hole will be repelled by positive terminal of the battery. So we can expect the hole to move down. And this electron will be repelled by negative terminal of the battery. So we can expect these electrons to move up. But the actual circuit is this one. Now we can understand very well that since there are many electrons in this region and the base is thin, of the order of 1 micrometer. Most of the electrons will go in upward direction. So the actual scenario is going to be this. And because the electrons are moving to the left, we have current to the right, which is IB. And if you can see here, the electrons are moving to the right, so I have current to the left. So I have this current IC. And this IC and this IB together will make this current IE. We can also understand that these electrons which are coming over here are easily attracted to the positive terminal of the battery. So for these electrons, it is a downhill trip. And since 95 to 99% of the electrons cross the base, so I can say IC is going to be alpha IE. And alpha is the fraction that has crossed the base, that is 0.95 to 0.99. So we understand that this IE is IB plus IC, and if I divide this whole equation with IC, we are going to get this one. And we already know that IC is alpha IE, so therefore on the left side we have 1 by alpha. IB by IC is called 1 by beta. Therefore we have beta as alpha by 1 minus alpha. Both alpha and beta are called current gain. So IC equals to beta IB, and we must remember this to understand transistors further. And also, because alpha is from 0.95 to 0.99, we can always calculate beta, and it comes out to be from 20 to 100. Right now we were talking about the motion of majority carriers. Now we will talk about motion of minority carriers. On the N side in the collector region, holes are the minority carriers. These holes will be repelled by positive terminal of the battery, so I can expect these holes to be moving down. So these holes are causing a current. We have just now studied that IC is beta IB. But we have one more current because of the minority carriers, and we call this current as drift current. So instead of IC equals to beta IB, we will have IC equals to beta IB plus I drift. But this drift current is so small that we can neglect it for all practical purposes. Now we shall write loop rule for this transistor. We can see here IBRB plus VBE minus VS equals to 0. VCE minus VCC plus ICRC equals to 0. That is the second equation. And of course, the third one we saw in the last slide, IE equals to IB plus IC. We can replace the transistor with its symbolic representation, which is this. Now, the transistor works in 3 modes: the cutoff mode, the saturation mode, and the active mode. So first of all, we are starting with the cutoff mode. In cutoff mode, we take Vs less than 0.7 volt. In that case, IB is going to be 0. I'll explain you how this is happening. IB is Vs minus VBE by RB. And for silicon diode, VBE is of the order of 0.7 volt. So for the current IB to flow, Vs must be more than 0.7 volt. And if it is less, IB is going to be 0. And because IB is 0, IC, since it is beta IB, is going to be 0. And since IE is equals to IB plus IC, therefore IE is also going to be 0. But theoretically, we may plot the graph as shown. Now you can see the graph. In this graph, I am increasing VCE to a very large value, and still there is some drift current, which is of the order of microamperes only. Therefore, this region is called cutoff region. We can see IC is almost 0 here. Saturation mode. Now suppose Vs is more than 0.7 volt and By some means, I have made VCE equals to 0. Then it is essentially a forward PN junction diode. You can see IC is equals to VCC minus VCE by RC. For IC to be maximum, VC must be 0. In that case, IC max is going to be VCC by RC. And this is what is called saturation current. So IC can never be more than VCC by RC. This is the input graph, the graph of PN junction diode. And this is the output graph. And in this output graph, we have put VC equals to 0, so we are at this. But we also remember that some drift current was flowing because IC was not just beta IB, it was beta IB plus I drift. Therefore, the graph will look as shown. Because I drift can never be 0, there will be some potential difference across C and E. If on calculation, if I get IC more than ISC, IC cannot flow, but instead we'll get ISC as the current flowing. When the transistor is used in cutoff mode and saturation state, it acts as a switch. Cutoff is off and saturation is on. Active mode. Suppose VC is increased keeping the same value of VS1, that is more than 0.7 as in saturation mode. Then in that case, the current IB is going to be Vs minus VBE by RB, which is going to remain constant. And because IC is beta IB, IC will also remain constant. In such a case, the graph will be like this. And this region is called the active region. If you understand, in the saturation mode we were here. If I increase VCE, no matter how much I increase, the current IC is not going to change because this current IC depends upon IB and IB depends upon these. And because I have fixed Vs, IB will not change regardless of what value of VCE we choose. Now suppose I choose a value of Vs more than the value of Vs1, then IC is going to increase because IB will increase and the plot will look like this. We can have many such straight lines depending on the value of Vs2. Early effect. This is after the scientist James H. Early. Suppose Vs is more than 0.7 volt, therefore IB will be flowing, and if I increase VCE, it will increase the width of collector base junction. So when the depletion width increases, the width of the base will reduce. If the width of the base reduces, lesser electrons will flow through the base. Because lesser electron flows through the base, it will reduce IB. And if IB is reduced, the collector current increases. And the value of alpha is IC by IB. Because IC has increased and IB has reduced, therefore alpha will increase. And if alpha increases, beta will certainly increase. So if I increase VCE, IC increases. Therefore, instead of having this horizontal line, we are going to have a slightly slanted line. So we have seen all the positive modes, but because of early effect and drift current, this is the result that we are going to get. NPN transistor used in an amplifier. Now you can see the circuit, and this is the diagram we are going to use again in amplifier, but instead of this circuit we have just added one AC source over here. We use transistor as an amplifier in active region, and for that VCE must be more than 0. Let's say Vs is 10 volt and EM, that is peak value of AC source, is 5 volt. Then the graph of input voltage will look like this. VAB is going to be E plus Vs, and E is 5, Vs is 10, therefore the maximum is going to be 15 and minimum is going to be 5. Because we have applied an AC source, this RBE is going to be dynamic resistance. Now we want to understand how does this circuit amplifies the input. The input resistance RBE is going to be change in input voltage by change in input current, which is the base current. So del V input I can write as del IB RBE. The output is going to be VCE, which is VCC minus ICRL, and if I differentiate this, I'll get del V output as minus del ICRL. Because we have a minus sign, I can say the output is going to be 180 degree out of phase of the input. Voltage gain. Voltage gain is surely del V out by del V in, and we know this del V out is del ICRL and del V in is del IB RBE, and del IC by del IB is going to be beta. We know that beta is from 20 to 100. So the amount of voltage gain will depend upon the value of RL. Higher the RL, higher the voltage. I have shown the output here, and you can see the output is 180 degree out of phase of the input. Output voltage is higher than the input voltage. Power gain. Power gain is current gain into voltage gain, and current gain at output is beta, and voltage gain is beta RL by RBE. Therefore, power gain is beta square RL by RBE, and we can remember this. Transistor as an oscillator. We can use transistor to produce undamped oscillation at the output terminal. And in this case, we are going to discuss tune-based oscillator. What you can see here, this is a soft iron in which we have two inductors L2 and L1 wound up. This inductor is connected to the capacitor here, acting as a LC oscillator. The tank circuit is an LC oscillator having frequency 1 by 2 pi under root L1C. The oscillating voltage across the tank circuit acts as an input signal. That means the current IB is going to vary sinusoidally. So I can say this is as good as an AC source. So I call this as an amplifier circuit, provided we have RL as a high value. Due to the oscillation of voltage in the tank circuit, the base current fluctuates sinusoidally. This in turn will cause the collector current to vary sinusoidally. Thus the output will also be varying sinusoidally. Feedback circuit. Now what happens? This current IC oscillates sinusoidally. So an EMF is generated in L2, and this EMF is fed back to L1 via mutual inductance. And if I am able to set the value of L2 in such a way that the energy lost by the wires in this L1C is the energy gained through the mutual inductance, then the oscillation will sustain. And that is what is the feedback circuit. In this case, two phase changes of pi takes place, one at amplifier circuit, another is due to mutual inductance. So in this case, the net phase change is 0. Or to say in other words, input and output are in same phase. Such a type of feedback is called positive feedback. Since the tank circuit is connected to the base side, it is called tune-based oscillator. If the tank circuit would have been connected to collector side, it would have been tuned collector oscillator. That's it for semiconductors. Thank you.